In section 6.3, we begin looking at a major part of calculus, which is problem solving. There's basically two major categories of word problems that calculus addresses. We're going to look at the first one here in 6.3, called optimization problems, and then in 6.4 we'll look at the other major category. So this is a very important part of the course. It's really one of the main reasons why we study calculus, is because it gives us the ability to approach these categories of problems. An optimization problem, the word optimum means you're looking for the best solution. So an optimization problem is a problem where you're trying to find usually the minimum or the maximum of a certain quantity. For example, you might be trying to build something for the minimum amount of cost, or maybe for the maximum amount of profit. Or you might be traveling somewhere and you want to get there in the minimum amount of time, or the minimum distance. Or building a part and you want it to be of maximum strength. So it's a very, very important strategy to have to be able to use calculus to solve optimization problems. So a couple things you might want to do before you start. On page 273, your textbook gives steps for problem solving optimization problems. You might want to read through those steps and try to follow them. I'll be using those steps as I work through these problems with you. Also, the math that's needed to solve an optimization problem is the math called of finding absolute extrema, which we did back in chapter 5.2. So it would be a good idea to also sort of go back and refresh your memory a little bit on how to find the absolute maximum and minimum values of a function over a given interval. So the first problem we're going to look at, I just call them number problems. They're not really that important, but they are good problems to begin our study of optimization. So what we have are two non-negative numbers. So basically, numbers that are greater than 0 have a sum of 20. So we have two numbers that have a sum of 20, and then the question goes on to tell us something about the numbers. It says, find these numbers if the sum of their product and 4 times one of the numbers is a maximum. What is the maximum sum? I find that the best way to start a word problem is making sure you understand it. So before we actually even do any of the calculus, the first thing is just to make sure you understand the problem. It's tough to set up equations and solve a problem if you don't really understand what it's asking. So what I like to do, especially when I'm first starting out word problems, is just play around with the question a little bit without introducing any variables. Just make sure we get what the question's asking. It says, find two non-negative numbers that have a sum of 20. So what does that mean? Well, two numbers that have a sum of 20 might be 2 and 18. 2 plus 18 would be valid answers in this question. Two numbers that have a sum of 20, and they have to be non-negative, so you couldn't have like -3 and 23. So just to get a feeling for the question, 5 and 15 would be possible answers. So if you just think about what the question's asking, we're looking for pairs of numbers that add up to 20, so you can see what the possibilities would be: 2 and 18, 3 and 17, 4 and 16, 10 and 10. After you reach 10, you just keep repeating yourself. Eventually you're going to have 18 and 2, which are the same two numbers. However, if we read on in the question, it says, find these numbers if the sum of their product. So again, let's just make sure we understand what that means. The sum of their product. So we want to add their product and 4 times one of the numbers. And we want that to be a maximum. So let's say, for example, we pick the numbers 2 and 18. So what does that mean? Well, it says the sum of their product. So 2 times 18 would be their product. And then we want to sum that, or add that, to 4 times one of the numbers. And we're looking for a maximum, so obviously we would multiply 4 times the bigger number. So let's go 4 times 18. So I've selected two numbers that add up to 20. I'm taking their product and adding it to 4 times the bigger number. And if you do that, it turns out to be 108. So what the question's asking is, it wants you to find these two numbers, and it wants this answer, this sum you get, to be a maximum. So in other words, is 108 the best we could do? So let's try 5 and 15. So if we go 5 times 15, so we're multiplying the two numbers together, plus 4 times 15, we get the answer 135. So obviously picking 5 and 15 would be a better choice in this question. Now we could just, in this case, the question is simple enough. We could just pick every possible combination of numbers that give us 20, and eventually we would find the right pair. But the purpose of this unit is to teach you how to do this mathematically using a combination of algebra and calculus. So again, the reason why I like doing this understand the problem thing is, at this point, you understand that in algebra, all we do is replace guesses with variables. So if you aren't sure how to set up a problem, this might give you an idea of what you're doing. When I picked 2 and 18, what did I do? Well, I just randomly picked a number. So let x be one number. That's the power of algebra, is we can assign a variable. We know we're looking for a number, and the number could be anything between 0 and 20, so we just randomly select the variable called x. Now the other number, when I picked 2, my 18 was determined for me, and it was determined by the fact that the numbers had to have a sum of 20. So what I do is I say, okay, if my first number was x, what would my other number be? Well, if one number is x, the other number would be 20 subtract x. Would be the other number. Okay, so now what I need to do is, so the first step is understand the problem. The second step would be identify your variables for what can change in the question. Well, what can change are my choice of the two numbers. Now we could have just said let x be one number, let y be the other number. Then we could have developed this 20 minus x, but in this case it's simple enough to just, I think everybody knows how we got the 20 minus x. Now the next thing to do is identify a formula for what you're trying to accomplish. Excuse me. You're trying to maximize the sum. So let's write a formula for that. We're trying to maximize the sum. The sum is equal to, now what did I do to find the sum? I took the two numbers and multiplied them together. Well, my two numbers are x and 20 minus x. And then I added that plus 4 times one of the numbers. Now, it doesn't really matter which one we pick. It makes sense mathematically to pick the x. It's easier to work with. So 4 plus x. So what I've tried to take you through in this question is, by understanding what the question is asking, we're simply replacing the numbers with variables. And then this formula right here, sum equals, is a function. It's a function that represents what I've illustrated right here. If we plugged 2 in for x, we would get this answer 108. Now back in section 5.2, we learned that if you have a function, you can find its maximum and minimum values by simply applying the theory for finding absolute extrema. But the next thing we have to do is we have to identify our domain. First of all, I'm going to simplify this actually. If we're going to eventually differentiate this, we should simplify it so we can distribute the x and just collect our like terms. And we end up with a function that says the sum as a function of x is equal to negative x squared plus 24x. Now this would be a parabola, and if we drew the entire parabola, it would be unbounded. But we are told that there are restrictions on the domain. The number has to be 0 would be the smallest number, and 20 would be the biggest. So we have to identify the restrictions. Our restrictions here would be square bracket 0 and 20. It might turn out that the best answers to pick would be 0 or 20. So what we do now is we've set up our problem. Now once the problem's set up, you're just now going to apply the math that you learned in the previous chapters. We're going to apply our algorithm for extreme values, how to find the extrema in a function. So what we do is basically two things. We know that the endpoints might be one possible solution. So what I'm going to do now is I'm going to find the sum at 0. Maybe the best answer would have been to pick 0 and 20. So if I pick 0, if I plug it into my function, I'm going to get negative 0 squared plus 24 times 0, which is going to give me an answer of 0. It makes sense that if one of the numbers is 0, that the other number, that if I pick 0 as my number, I'm going to end up with 0 times a number plus 4 times 0. Obviously, that's not going to give me a very large sum. If I pick 20 as my number, you might think that's the same thing, picking 20, but remember that we're multiplying one of them by 4. So if I pick 20, I'm going to get, if you plug it into our function, we're going to get negative 20, negative bracket 20 squared plus 24 times 20, which turns out to be 80. Well, we can see by just looking at our examples here that we did that obviously we can do better than 80. So the numbers shouldn't be 0 and 20 or 20. So we've evaluated our endpoints. Now we have to evaluate what are called the critical numbers. And again, you may have to go back and look at this. We looked at critical numbers back in the previous chapter. Critical numbers are any points where the derivative is 0 or the derivative is undefined. So what we do now is we differentiate our function. We differentiate s, so s prime. And again, the theory here is when you take the derivative, you're finding tangents. And we're looking for the place where this graph is at its highest peak. If you actually graph this function, if you graphed sum versus your choice of number, the graph is going to reach at some point a peak, and that's where the derivative is 0. So what we do is we differentiate the function. So we go s prime of x, and we get negative 2x plus 24, just simply by taking the derivative. And then we make the derivative equal to 0. So we make it equal to 0. And this one ends up being a fairly simple equation to solve. We just move the 2x over and divide by 2. And it turns out that x is 12. Now, according to the theory we learned back in 5.2, the absolute extreme on a graph must occur either at a critical point or the endpoints. So let's test our critical point. Let's find the sum at 12. So we're going to plug 12 into our sum function. And if we do that, we're going to get, so we're going to plug 12 into this function right here. And we're going to get 144 if I did my calculations correct. So we end up with 144. So 144 was better than the 135. And now we know for sure that we couldn't have done any better than 144. So the question asked two things. It said, first of all, find the numbers. So obviously the numbers are 12 and 8 would be our two numbers. And the question also wanted us to find the maximum sum. Well, the maximum sum we already found is 144. Now, I'm running out of room on my sheet here, but a person really should answer the question with a sentence. And so you would just answer that the numbers are 12 and 8, and they have a maximum sum of 144. Okay, the next optimization problem we're going to look at falls into the category of what are called area problems. In this case, a farmer wants to build a rectangular pen. And the cost of building the pen depends on which side of the border is being built. The material for the north and south costs more, $10 a meter, while the material for the sides, the east and west, costs $3 a meter. You know, the north and south, the north might have a gate in it or something, or some material to make it stronger for that reason. So that's why you might have a difference in cost. Find the dimensions that will minimize the cost of construction. So obviously the farmer wants to build this fence enclosure for the least amount of money possible. But the condition is it has to have an area of 270 square meters. So again, if you want to just try to understand the problem, so what could the farmer do? I mean, they want to build a rectangular fence. So there's the rectangular fence. And it has to have an area of 270. So for example, they might choose to make this 10 and this 27. 27 times 10 would give us our area of 270 meters squared. But you can see that there's an infinite number of possibilities. They might choose to build the fence so that it was maybe longer and narrower. It might only be 5 meters on the east and west sides, and then 54 meters on this side. Obviously, we can increase or decrease the 5 and 10 as much as we want, as long as we compensate with the north and south sides by making them longer or shorter, as long as they give us a product of 270 square meters. So what we're trying to do is we're trying to find the minimum cost of building this enclosure. So now that we understand the problem, we want to assign our variables. In this case, I think the picture is kind of important. In some of these questions, a diagram is sort of essential. So what would the pen look like? Well, in general, it would just be a rectangle, like that. And the variables are going to be the numbers that we choose for the sides. I just randomly selected 10 for this one. So in general, what I could do is I could just say, okay, let's say that that this was y, and then this was y. I could choose to let the other dimension be x. The power of algebra is all you're doing is replacing variables with guesses. So I'm just saying that let x be, and I don't insist that you write a let statement. The diagram would be sufficient, but you could say let x be the length of the north and south sides and let y be the length of the east and west sides. But your picture says that, I think, well enough. Now the area has to be 270. So one thing that we know for sure is that the area, x times y, has to be 270. That's going to come into play here. Obviously, is one of our restrictions in the question. So what is the goal of the question? Well, we're trying to minimize the cost. It's always a good idea to identify your goal. In this case, you're trying to minimize the cost. The cost we'll just call C. So what you need to do now is write a function. What is it going to cost to build this enclosure? Well, the cost C is going to equal, we're told that the material for the north and south is $10 per meter. So if we're going to use X meters here, it's going to cost us $10 times the number of meters X. It's also going to cost us 10 times X for the other side. So these two sides right here would cost 10X plus 10X. And then the two east and west sides are going to cost $3 per meter, so 3y plus 3y. So we end up with a cost function. The cost of building this fence is going to be 20 times x plus 6 times y. Now when you're doing an optimization problem, you're going to have to differentiate this function. So your function has to be a function of a single variable. We need to determine what the cost is as a function of, let's say, just x. So something is linking the x and y together. And what's linking them together is that the area has to be 270. Whatever you choose x to be, you can't just randomly pick a number for y. The number for y is going to have to be whatever gives you a product of 270. So what I'm going to do here is I'm going to isolate the y in this formula. The y is just going to be 270 over x. There's no magic to why I chose to isolate the y. You could have isolated either variable. I just want my function to be a function of x. So now I can go back to my cost function, and I can say the cost is going to be 20x plus 6 times 270 over x. And now I've developed a function that gives me the cost as a function of one variable. So the cost of building this fence as a function of x is going to be 20x plus, if you multiply the 6 times 270, you just get 1620. Now this is going to be over x, which would require a quotient rule. So it's beneficial in this case at the top, and just write it as 1620 x to the minus 1. Now the restrictions in this case are a little difficult to get a handle on. The area has to be 270. Theoretically, even though it would be silly, you could build this fence to be, let's say, 1 meter wide and 270 meters long. If you kept going with that, you could build it half a meter wide, as long as you compensate by making this 540. So in theory, what you could do is you could make the x infinitely small or infinitely large. Now, obviously, in those cases, your cost would be astronomical. If you did choose to make the x, let's say, or the y, let's say 1, you'd have to have 270 meters of fencing on the front and 270 meters of fencing on the back. If you chose to make y, let's say 1/10 of a meter, then all of a sudden these would become 2,700 meters. So what's going to happen is your restrictions are going to be round bracket 0 to infinity. You couldn't actually make x 0 because then there wouldn't be a rectangular enclosure, but you could theoretically make x approach 0. As silly as it sounds, mathematically, you could make the rectangle so that it was only like 0.000001 meter wide, and then compensate by making it longer, as long as you get a product of 270. Now, in the case when you have round brackets, we don't have to test these endpoints because, first of all, there are no endpoints, and we know that if we approach them, our cost would just become a maximum value. And so, in this case, the endpoints are not significant. We do have to identify them, but in this case, we don't have to test them. So that means that the answer to this question is going to be wherever the derivative is 0. We just need to find critical points. So we're going to differentiate C prime, which will be 20 for the 20 times x. And this is just a power rule now that I've moved the x to the top. So it's going to be minus 1620, and then x to the negative 2. Now x to the negative 2, I just soon move that back to the bottom and just write it as over x squared. Make that equal to 0. And the reason why I want to make it equal to x, or move the x squared to the bottom, is because now to solve this, I'm just going to move the negative 1620 to the other side. 20 equals 1620 over x squared. And now I can put this over 1 and cross multiply. So I'm going to get 20x squared equals 1620. Divide by 20, we get x squared equals 81. So x is equal to plus or minus 9. Now our restrictions are positive values. You can't have a negative fence line, so we can ignore the negative value. So our answer is just going to be 9. Now the theory we learned back in chapter 5 guarantees that this is going to be the best answer. We know that the absolute extrema, the maximum or the minimum value of a function, will either be at its endpoints, in this case it would be the maximum values, or a critical point. So we know that x is going to be 9. We can find y. Y is just 270 divided by x. So 270 over 9 is 30. And we've just found the dimensions of our rectangle. The rectangle that the farmer should build to minimize the cost, x should be 9, so the front and back should be 9, and the side should be 30. I guess I didn't draw that very well to scale. It makes more sense that you'd want to have shorter front and back because they're a higher cost. And it turns out that that's what the farmer should build, is a fence that's narrower on the front and longer on the sides. And again, I didn't draw that very well. I apologize for that. So the dimensions would be 9 meters by 30 meters. And the question didn't ask it, but if we did want to find what is the minimum cost, we would just find the cost, C, at our critical point, which is 9. So if we plug 9 into our function for C, we would get 20 times 9 plus 16, and then over 9. I just moved the x back to the bottom for the sake of that calculation. And it turns out that that would be $360. So you can see how important these optimization problems are. This obviously is an oversimplified question, but in industry, we're always interested in trying to minimize the cost of producing something. And optimization problems give us a strategy for doing that. Okay, the last problem we're going to look at in this optimization section, are the last category, are called volume problems. And the example I'm going to do is sort of a classic problem in calculus. I remember this question when I was in university. It was asked on the final exam because it's sort of your standard volume question. You want to put some kind of, in this case, pop into a cylinder. And the pop has to hold 400 milliliters of pop. And the question is, how should you build the can if you want to minimize the amount of material used? Obviously, it costs money to build the can using material, and you want to do that for the cheapest way possible. If you ever wonder why a Coke can or a pop of some kind is shaped the way it is, you can be guaranteed that someone's figured out the cheapest way of doing it. So the question says a pop can is to hold 400 milliliters. Find the dimensions of the can if the amount of material is to be minimized, and I apologize for the scribble there, but that word is minimized. So first of all, just understanding the question, like you want to build a pop can, so it's going to look something like this. It's going to be a cylinder. But your variables, like what can you change? Well, you could build the can to have a smaller top and build it taller to still hold the 400 milliliters. Or you could build the can to have a fairly large front and bottom, or top and bottom, but a fairly small height. So what we can change in this question are the dimensions of the can. And the dimensions of a can are its radius and its height. So what we have here is just a cylinder. And the cylinder has a radius r and a height h. Those are our variables in this case. So what does the question want us to do? It wants us to minimize the material. The material is the surface area of the cylinder. So we want to minimize, I'll call it S for surface area. Now the surface area of a can, it's going to have a top and a bottom and of course the sides. Now I don't expect you to know the formulas, so on a test those will be provided for you. But the formula for surface area of a can, the can is going to have a top to it. The top is just a circle, and you probably know the area of a circle is pi r squared, and the bottom will also be a circle. So the surface area is going to be 2 pi r squared for the top. Now if you actually unfolded it, if you actually sliced the can down the side and unfolded it, a can actually unfolds into a rectangle. You can imagine taking a sheet of aluminum like this and just rolling it up, and it would be in the shape of a cylinder. So the actual can itself, this part right here, if you unfold it, would be a cylinder, would be a rectangle. The height of the rectangle would be the height of the cylinder, and the length of the rectangle would be the distance around the circle on top, which is the circumference, which is 2 pi r. So the area, the surface area of the sides of the can are going to be the area of this rectangle, which is 2 pi r times h. So the surface area of a cylinder is 2 pi r squared for the top and bottom, plus 2 pi r h for the side. And there's our function. And our goal is to minimize that function. You'll notice that it has two variables. Often in these questions you have that problem of two variables. So you have to ask yourself, what's linking the radius and height together? What in this question is constraining us to not build it of any size we want? Well, what is happening in this case is it has to be 400 milliliters. So no matter what we do for the radius and the height, they have to be in a certain proportion so that they give us the volume we want. So what's linking the variables together here is the volume of the can. Now the volume of a cylinder is simply the surface area of the top times the height. So the volume of a cylinder is pi r squared h. That pi r squared h has to be 400 milliliters. Now you may know that milliliters are just centimeters squared. So our units here are going to be in centimeters. Now we have to make a decision on getting rid of a variable. So in this formula we need to get rid of either the r or the h. It'd be simplest to get rid of the h since it only appears once. So I'm just going to isolate the h, and I'm going to get 400 over pi r squared. The key in almost all of these optimization problems is finding a relationship between your two variables. In this case, it's the volume. So I can now plug that back into this formula, and I will get the surface area S is 2 pi r squared plus 2 pi r times 400 over pi r squared. And there we have a formula now that gives us the surface area as a function of radius. So we've created a function that we need. Now we're going to simplify this a bit. We're going to have to take the derivative. So this is kind of awkward to work with. So we're going to write it as surface area as a function of radius r is going to be 2 pi r squared plus, now I can multiply the constants together. The 400 times 2 will give me 800. The pi's will cancel, and there'll be an r on the bottom, which I'll move to the top and make r to the minus 1. Now the restrictions are just like the restrictions we saw on the previous question. In theory, there's nothing stopping you from building a cylinder of infinite height or infinite radius. You just have to compensate by making the other variable infinitely small. So our restrictions are going to be 0 to infinity, and in that case we'd actually be using a lot of material, and so we're going to ignore those restrictions. So there's our formula. So now we just have to differentiate. We know that the optimum solution is going to be at a critical point, so we differentiate s prime of r. 2 pi is a constant, so when we differentiate, it's just our power rule. So we just multiply the 2 out front. So this would be 2 times 2 pi r to the 1, or just I should have just written it as 4 pi r. When we differentiate 800 times r to the minus 1, the r to the minus 1 is a power, so we multiply the minus 1 out front, so we get minus 800. And then we subtract 1 from the exponent, which will give us r to the minus 2, or we'll just put it over r squared. And then, of course, we know to make that equal to 0. Now, we solve this exactly the same way we solved the previous one. We're going to move this over and cross multiply. So we're going to get 4 pi r equals 800 over r cubed. Cross multiplying, we get 4 pi r, sorry, this is r squared. I got ahead of myself. That's going to be 4 pi r cubed equals 800. Divide both sides by 4 pi, and we get r cubed equals, if I divide 800 by 4 pi, I'm going to get 200 over pi. And then take the cube root, and we get the cube root of 200 over pi. Now, the cube root of 200 over pi, of course, is an irrational number. So if you wanted to leave it as an exact answer, then that would be your radius, but that doesn't make a lot of sense to most people. If you were to tell somebody that your soda can had a radius of the cube root of 200 over pi, they probably would look at you quite strangely. So we're going to actually change it to a decimal. If you actually work this out, it works out to be approximately 3.99, or we can just say approximately 4 centimeters. Our height, we have a formula that relates height and radius. It's right over here. Our height is going to be 400 over pi times the radius, which is approximately 4 squared. And if you work that out, it turns out to be approximately 7.95, which I'll just round off to approximately 8 centimeters. So it turns out that you should build a can so that the radius is 4 centimeters and the height is 8 centimeters. It turns out that you cannot build a can for any less material than those dimensions. Now, in real life, if you were doing this question, there would be other factors that would go into the cost. Usually a can has printing on the sides or a label on it. The top and bottom might be of stronger material. You might have the actual flip thing that you open the can with. So in reality, there's more factors that go into doing this, but the principle is the same. You need to write a function that gives the cost of building this can. In this case, we just kept it simple and made it just surface material. And so that would be the dimensions of that can. So that wraps up our section on optimization problems.